Greetings. Our group is working on a continuous fiber extrusion and effector. This means an attachment for a robotic arm that can automate 3D printing fabrication. In this video, we will discuss the following aspects of the project. First, how we will ensure that our project can succeed globally. Next, the standards considerations taken to ensure that our project is compatible with international standards. Then the feasibility analysis to ensure that our proposed project is realistic and attainable. Next, an analysis of possible issues and risks faced during the project and how we will deal with them. Then our plan of action to show how we intend to realize the project. Following that, multidisciplinary aspects and personnel and the different perspectives and expertise that our members bring to the project. Then our budget, which deals with how our project is working with the FIU Robotics and Digital Fabrication Lab. And finally, end product description and other deliverables. We will describe the specifications and characteristics that we expect our end project to achieve. So firstly, for globalization, it is vital for a project to succeed not only in this region, but globally. We believe our project can succeed everywhere because it fulfills a need which is common across industries throughout the world. That need is to improve manufacturing processes with more efficient and cost-effective methods. Because our project has to appeal to different cultures and nations, we are committed to ensuring that our project develops guidelines to ensure that worker safety and dignity are respected, as well as operational guidelines for workplace safety and ethical suggestions to ensure that the materials chosen minimize damage to the environment. Our project has the advantage of having different perspectives because 2 of our team members are international students. We also reached out to 2 persons from different countries, namely from Guatemala and Chile, to hear their thoughts and reception for the project. Our contact from Chile noted that his country is always eager to embrace and invest in new technological advancements, which is why he is sure that our project would be well received in his country. Our contact from Guatemala was hopeful that projects like ours could lead her government to incentivize foreign corporations to invest in automated fabrication plants in her country. Now we will discuss standards considerations. We plan to comply with international trade standards to ensure that our project is compatible and accessible to all fabrication plants throughout the world. We will ensure that our project is not limited by trade barriers or national borders. The field of robotic end effectors, which is to say accessories attached to robotic arms, is very modern and an emerging field. Because of this, there are few available standards and guidelines to follow for their construction. However, the ISO, the International Organization for Standardization, does offer a few standards for robotics. Our team is committed to following these 3 standards, which are specifically for robotic end effectors. First, ISO TR 20218-1-2018. This is a standard which guides how to manufacture, design, and integrate end effectors to ensure that they are both safe to operate and universally compatible. So it's the most relevant specification for our project. The next standard is one which governs how to properly describe the technical details of our project, including terminology, symbols, and descriptions. This ensures that any person throughout the world who reads about our project understands exactly how it works. The next standard is simply an update or an extension to the previous standard and is still currently in development. This standard is currently being developed because the previous standard was published originally in 1996 and the field has advanced greatly since then. Our team is committed to following these 3 standards to ensure that our project is universally compatible and accessible and therefore successful.
Hello everyone, welcome to Team 32 on presenting the fiber extruding robotic arm project. My name is Hong and I will be guiding you through the feasibility analysis and risk analysis. So let's begin by feasibility analysis. I classified the project feasibility into 7 sections: technical feasibility, resource feasibility, economic, scheduling, legal, marketing, and cultural feasibility. The technical feasibility sections is used to determine the viability of the project early by examining the available of the project. In that technology, it is not readily available. Alternative tools must be adequate, prepared to complete the project. So as you can see here, there is a table that I made that is have 3 attributes for the table with a total of 11 and the average of 3.7. Now let's come to resource feasibility. Refers to an analysis that include team member capability, knowledge, and skills, and how those attributes help us to create, develop the products. The design team must be made up of people with the skills and knowledge necessary to create the products. Here I divided into 4 sections with a total of 17 and the average of 4.25, which is considered as a good point. For economic feasibility, analyze the debt and the financial costs associated with the project. Assessing the monetary debt before project commencement is the correct way to attract the investors' interest. For these sections, I divided onto 2 attributes with the total of 9 and the average of 4.5. For scheduling feasibility, a schedule feasibility assessment is an essential step in assessing a project's viability in a limited time. The feasibility of the schedule will help us on precisely know when the project will be complete. In the table here, I divided into 3 sections with a total of 12 and the average of 4. Legal feasibility may occur. It refers to legal problems that may occur using the product. The product duplications may also occur if the product is quite similar to the previous created effects. In here, I divided into 2 sections with a total of 9 and the average of 4.5. For marketing feasibility evaluates the feasibility of a product through a customer taste. This product's process will help us assess whether the product is worth it or not. This assessment is critical because it will help us as a team to understand the customer's psychology while improving accessibility to the customer. Here I divided into 3 sections with a total of 14 and the average of 4.7. Cultural feasibility refers to analysis help us to determine the acceptability of the product to the public. The public's acceptance will affect the inventor's consumptions of the product. If this project causes an infringement on the life or interest of the public, it could be the downfall of this project. So here I divided into 4 attributes with a total of 14 and the average of 4.7. Now let's come to a ranking of the feasibility. Here I divided into 4 levels of ranking: equal importance, moderate importance, strong importance, and extremely more important, with relative score as 1, 3, 5, and 7. Here there is a table that follow the formula GMs and the weight that calculated. I divided this is the score the grades that we have concluded. For technical is 1, resource is 3, economic is 5, schedule is 5, culture is 7, legal and marketing is 5, which is come to the total of 9.36. And here is the weighted score table, which is calculated based on the weight and the score. The weighted score is calculated using the formula G weight equal GM divided by the total. Now let's come to a risk analysis. We divided into 7 sections, which is schedule, culture, legal, marketing, economic, resource, and technical, which are the aligned problems with it. For schedule, there is a procrastination, scheduling classes and job, while another trouble is scheduling trouble due to the group members living in different time zone. For marketing, for instance, like marketing, there is 2 main risk that could cause to the downfall, which is the product must be compatible price to adjust the income of the customer, and the design, the functions of the project must adapt to the taste of the customer. Here is the fault tree that we have come and analyzed. We have come with the E, S, C, L, M, R, T represented as the risks, and this could help us to keep track on what could be the risk that caused to the project could not complete it on time. Now let's come to the risk exposure matrices. Here there is a table here, the likelihood of occurrences. I classify it into 4 classes, which is related to low, moderate, severe, and catastrophic, with 4 level of likelihood, like very likely, possible, unlikely, and legends. And this is the table of actions that come for each solutions and each class. You can see here that I classify it into different color, which is represent the importance of it. When it's come to the red, which is like very likely to be happening, and it could be like a serious problems, such as for the T1, which is the technical problems related to the problems of hardware malfunctioning due to a lack of knowledge. This could cause the hardware to be broken or be malfunctioning. And the solution that we have come to is contact the supplier immediately when the malfunctioning occurs. Thank you for listening from my part.
My name is Duque, and today I'm going to be presenting our Group 32's plan of action. So, for our team to be more organized, task-oriented, and responsible, our team is going to need a plan of action. The plan of action consists of multiple parts. The first one being a statement of work, a workbench breakdown structure, and a Gantt chart. The other two we're going to be discussing in the next 2 slides. So for the statement of work, it usually covers the scope of the project, the location, and the time period, and the responsibilities of each team member. So now we're going to look at the work breakdown structure. So this is our team's workbench breakdown structure. To the left, you can see our main project, which is called the Robotic Arm and Effector Continuous Glass Fiber Extruder. So as the name implies, a workbench breakdown structure breaks down our project into 5 main phases with each its own subtask. This allows us to see how much progress we need for our project and how many parts it takes to complete each phase. So for this project, we have 5 phases. For the first one being the project research, which is 20%. The second one being the hardware design, which is 30%. The third one being the software design, which is 30% again. And the developing and testing, which is 15%. And finally, the product overview, which is 5% of the whole project. So our project consists of 5 phases with each its own subtask. Once again, this is a way to see how much our project takes and how long it will take us to complete it. Now for the Gantt chart, we can see here is a WBS breakdown structure chart, but the difference is it has its own time periods. So as like the WBS chart, we can see on the left side each phase and each subtask of the project. But the difference is we can see the start date and end date. So for the phases, it's in orange, how long of a time period it will take to finish, while the subtasks are in gray. So it's a visual way of seeing how long our project will take and what time period it will take. So our team has deadlines and are more responsible for the project. So for the multidisciplinary aspect and personnel, our team needs different specialized skill sets that will allow us to adapt and complement each other. So for our team, we have 4 members: me, Christopher Duque, Daniel Simkins, Tran, and Gustavo Ramirez. So for me and Gustavo Ramirez, we both specialize in the hardware component of the project. Since I have prior experience in nanotechnology and some chemistry, Gustavo Ramirez has knowledge in 3D software. So we both have some specialty on the hardware components of the project. while Tran and Daniel Simkins both have experience in coding and computer softwares. So they'll both be responsible in the software component of the project. Hence, our team has different specializations for the project and that will complement each other for the future. So overall, our team has decided to give Daniel Simkins leadership. This is mainly due to his prior experience in a STEM research tutoring class.
Hello everyone, my name is Gustavo Ramirez and I'm going to be covering with you the budgets and product descriptions and other deliverables for this project. To start off, we're going to be looking at the budget. It is really important to have a budget as it allows us to calculate how much funding we're going to require to complete this project. Having a budget also allows us to have a faster purchasing time and make sure that we don't purchase anything that's not essential towards this project. The patent costs are going to cover everything in between from lawyer fees to actual fees that have to pay to the state or government to have it implemented. Next is our machine calibration costs. Our machine calibration cost consists of the 3D printer testing. This allows us to ensure that our machine is working properly before we announce it to the public. Following this is the design cost. It is important to have a clear hardware design as well as a software design. For this, our total is going to be $750. For our equipment costs, this includes anything that has to do with the assembly tools, the fiberglass filament which is going to be used to do our 3D printed products, and our extruder which we're going to be building. For this section, we decided to do a multi-level breakdown of our project, going from level 0 being the most basic description and generalized description to level 2 being the most in-depth and exhaustive detailed description. For this section, in the level 0 diagram, we have our 3 inputs: power, executable commands, thermoplastic filament. And then in the center, we have a robotic arm and effective continuous glass fiber extruder, which then leads us to our output, which is a 3D printed product. Like I stated before, this is a very generalized description of what's going on. For our level 1 diagram, we have some new components being introduced, such as a KRC4 compact controller, the robotic arm, filament distributor, and the extruder. We have our inputs being the power, the executable command, and thermoplastic filament. So here we notice that the power and the executable command is going to the top of the flowchart, which goes into the KRC4 compact controller, which is then activated and transmits the coding into the robotic arm to then initiate the movement that's going on, which we're going to be discussing in the next slide. For thermoplastic filament and our power is going to be going to the filament distributor. This is where the rolls of material get placed and moved onto the extruder, which then gets melted, and working simultaneously, we have our 3D printed product. In our level 2 description, we're going to be using 2 different diagrams. One to see what's going on in the background of the robotic arm, and one to see what's going on with the extruder. Here we have presented the robotic arm and what's going on all around it and who's involved. We still have 2 inputs here. We have the executable commands and the power. Once this goes in, we have our smart pad, which can be controlled by a user, and codes can be generated and transmitted to the KRC4 compact. This can be used either manually or uploaded code. Once it reaches the KRC4 compact, it is then translated into movement commands, which is then sent to the robotic arm. Ultimately, what the function that we're accomplishing here is the movement for the design is being executed. For our other level 2 diagram, we're going to be looking at the portion that has the filament distributor and the extruder. Here we only have one input, just the filament. It's going to be going to the filament distributor, which then gets passed on to the roller feed drive instead of the extruder, which then goes into our heat sink, which starts creating a temperature high enough for the material to become more malleable. The temperature sensor assures us that it's not getting too hot nor too cold. Once it goes to the extruder nozzle, it's going to begin getting placed on the fixed building plate. The fixed building plate is where its last destination is at, meaning that we're going to have our 3D printed product after all the functions are executed. Finally, we come to our section of other deliverables. In this section, we have our user manual and our video presentations. Our user manual is going to be created once our project has been completed and open to use. In our manual, we're going to have little tips and tricks and steps as to how to activate the machine and work with it. For our video presentations, it's going to cover similar things in shorts, such as how to video presentations, and it's going to be updated as we discover new obstacles that we encounter. In conclusion, Our team is ready to move forward with our next step of building this project. We have done a deep analysis of every aspect needed to implement this project, going from global trade laws to making a budget to see where we need to be by a certain time and date. We have a clear understanding of how our project will work, and we have clear deadlines and goals set. Not to mention the complementary knowledge and skills that we have within this team. Thank you for watching.